In this section, we're talking about the area of triangles. The area of triangles is based on the area of parallelograms. If you look at a parallelogram, you'll notice that it is made up of a base and a height. The area of a parallelogram is determined by multiplying the base length of your parallelogram times the height of the parallelogram. The height is the perpendicular distance between the bases, and the bases are the parallel sides. So this top line is a base, and this bottom line is a base, and then the line that connects them that's perpendicular to both of them is referred to as the height. So if you multiply one of the bases times the height that it's perpendicular to, you'll get the area of the parallelogram. Now in the next picture, what we see is that if you have any parallelogram and you split it in half by joining opposite vertices, you actually end up with two congruent triangles. Therefore, the area of any triangle is half the area of the parallelogram. So we can say the area of a triangle is 1/2 base times height. So the first thing that's important is being able to recognize bases and heights in triangles. In order to identify the base and height in a triangle, you can draw a line from any of the three vertices. So I'm going to start with this vertex. And if I draw a line straight down, it would cross this imaginary line that's an extension of the bottom side of our triangle, and we would consider that our base and the red line our height. Now we don't consider this imaginary line as part of the length of our base, but we do understand that the red height is perpendicular to the base even though they don't actually touch. In this next example, I'm looking at this vertex on the bottom right, and if I connect it with the opposite side, I can connect it in such a way that the line is perpendicular to the base. So the line always has to go from one vertex to the opposite side, or an extension of the opposite side, and it has to be perpendicular to that opposite side. So just like with parallelograms, base and height must always be perpendicular. The same holds true for triangles. So let's look at some examples of finding the base and height. So here we're going to drag the height to connect to an opposite vertex and base. So in this first example, this was like one we already saw. Here is a vertex, and we're drawing a line perpendicular to this side opposite. In this next example, this is a right triangle. So this would be my height, and this would be my base. And since it's a right triangle, they form a right angle, so those two sides are actually the height and the base. Which, by the way, when you have a triangle, it really doesn't matter which sides are the bases and heights as long as they form a right angle. So you could, if you have the two numbers and you're multiplying them together, it doesn't matter which is base and which is height. In this next example, this is also a right triangle. It's just rotated. And so one of these sides is base and one of these sides is height. It doesn't matter. I drew this one as the height and this top one as the base. In this next example, I have an isosceles triangle, and I drew from the top vertex down to the side opposite. And that gives me a perpendicular distance, so that's the height, and the bottom line is going to be my base. In the next example, I have an obtuse triangle, much like the first example, and I picked this top right triangle's vertex, and I drew a line down perpendicular to the opposite side, even though that side will not extend to the height. I can imagine it, and so I can see where the height is. Now, one thing that's kind of interesting is with triangles, you have either 2 or 3 heights. So for each vertex, you're going to have a height that connects to the other side. The only example where we don't have that is a right triangle, because the base and height are going to be the same thing regardless of whether you're looking at this top vertex or this bottom right vertex. In either case, the base and height are the same. So you only have 2 heights when you have a right triangle. For the rest of your triangles that are not right triangles, you'll have 3 heights. So let's look at some examples. In this first example, we have an obtuse triangle. And so we have a vertex that we can carry across to the opposite side. And then the top vertex we can take down, and then the bottom right vertex we can take up to find the height. And you can almost see the parallelogram that this is cut out of, and the base and heights within it. In our next example, you'll see the right triangle as I mentioned. You can only have, well, you can think of it as having 3 heights, or you can think of it as the base and height are interchangeable, so it only has 2 heights. Either way is fine. Again, I have the right triangle and all the different ways I can look at bases and heights. Then the isosceles triangle. I like this triangle because it forms like a little star in the middle. The top vertice going straight down to the opposite side. And then you have the bottom left vertice going over to the opposite side, and the bottom right vertice going over to the opposite side. So all of those will form heights with the opposite side being the base. And then lastly, I have an example of an obtuse triangle. And on the obtuse triangle, this vertex is coming across to this side right here, and they're perpendicular. This side and this vertex is coming across to its opposite side. And then this last vertex is coming across to this side right here, which is perpendicular. So let's look at some examples. Here I have where we can clearly see that we have a rectangle split into 2 congruent triangles. So it's pretty easy to see that the width is 3 and the length is 4. So for the whole entire rectangle, the area would be 3 times 4, or 12. However, we're finding the area of the triangle, which is half of that. So half of base times height would be half of 12, or half of 4 times 3, which is 6. And the next triangle, I have a rectangle as well. A cutout of that is an isosceles triangle. Now in this example, counting the blocks is kind of hard as far as trying to add up the area. So I'm just going to use the blocks to help me determine that the length is 4, the width is 3. Again, it's 1/2 base times height. So that's 6 centimeters squared. And area is always units squared. In this example, we have 1/2 base times height. And again, 96 is the perpendicular distance from the top vertice down to the opposite side. So that gives us 2,784. I'm sure you'll take my word for it. We're just putting that straight in our calculator. In the last example, it's important to be able to determine what is your base and what is your height. So see if you have any clue as to what's perpendicular. Well, there's a perpendicular symbol here, which means that this is an important line. It's going from a vertex to the opposite side, and it's perpendicular. So that must be the height, 8. And the side it's perpendicular to is 6. So it has a length of 6. So 1/2 8 times 6 is 24.